The resolution of a digital to analog converter is the number of discrete values that the digital input can accept, and this is often given in the number of bits associated with that digital to analog converter, with that DAC. So this is very similar definition to an ADC as a DAC. So a 2-bit DAC, for example, would give you 2 to the 2 or 4 different possible input codes and also 4 different discrete output voltages or output currents. DACs can occasionally output a current as well. Similarly, an 8-bit DAC would give you 2 to the 8, or in this case 256 discrete outputs. So in addition to defining this as the number of possible inputs, because those inputs are mapped to a single output, it also defines our number of outputs from our DAC. So typically on a microcontroller, you're going to see DACs that are on the order of maybe 8 to 16 bits, and most typically in the 8 to 10-bit range. For the audiophiles out there, you can often find 20 to even 30-bit DACs, and I'll say the 30-bit DACs are a little crazy, but 20 to 24-bit DACs are reasonably common in audio equipment, right, where you're really concerned about the fidelity and the precision and accuracy of the audio files that are coming out to your headphones. So the least significant bit of a DAC is going to be the change of the output, say a voltage, that's due to a change of the input code by a single bit. So once again, fairly similar, but in reverse to our definition of least significant bit for an ADC. So for voltage output, we can define a VLSB that's equal to our full scale range divided by 2 to the number bits, 2 to our resolution. So effectively the smallest change that I'll have in my output voltage. So a couple quick examples of this. If I had a full scale range of 4 volts, say, and only a 2-bit DAC, then I would have a least significant bit in this case of 4 volts divided by 2 to the 2, or 1 volt. And that's effectively saying I'm going to have 1 volt levels between my output. Maybe I start at 0 volts, I go to 1 volt, 2 volt, 3 volt. Or maybe I start at 1 volt, 2 volt, 3 volt, 4 volt. Right? So those are my possible outputs. Now if I instead had m equals 10, I'd be looking at a least significant bit in that case of 4 volts over 2 to the 10, or 1024, or about 3.9 millivolts. So obviously much closer to the ideal, ideally I'd like a continuous output if I have a higher number of bits. So the smaller my least significant bit, the closer I approximate the ideal conversion. So similar to the challenge of quantization error that we saw in an analog to digital converter, we're going to have a number of sources of error going from our digital to our analog side as well. And all of these are going to stem from some diversion from that ideal conversion that we talked about. So my ideal conversion would take me from some digital code to some V out, for example. And I'll start with the idea of offset error. And an offset error is going to stem from the fact that I might have a shift in my output. So my code 0 does not correspond to 0 volts. And when measured at code 0, this is called the offset error. And I'm going to write it as E0 or EO. So another error going from my digital input to my analog output can stem from the fact that I might not have the same VLSB each time. I might actually have some gain error associated with this. So most often this is measured at the highest point here. So I'm going to call this EG, or gain error. And typically that's measured at the code 2 to the m-1, effectively the largest code I can have. So obviously that's giving me some kind of bound on that error. If I have a smaller code, I'm going to have a smaller error associated with that. So the final sources of error that I'll talk about, and obviously there are more that can come into play here, are going to be nonlinearity errors. And there are two primary types of nonlinearity error. First one is going to be INL, which is our integral nonlinearity error. This is effectively our code spacing. So we'd ideally like our codes so that our output voltages are always different each time, but sometimes we might get some examples like this where different codes will have the same output voltage. And that's our integral nonlinearity error. The other nonlinearity error is going to be the DNL, or differential nonlinearity error. And these are effectively the voltage step heights and the difference that I can have here. So for example, these are much smaller. The difference between these two codes and the output step there is different from these two codes and the output step there. So that is effectively our DNL. And to get some sense of what kind of magnitude those errors might be associated with it, this is our Arduino from the datasheet for the microcontroller that's on that Arduino DWE. And I can look at my various errors here. So my offset error right here is going to be typically plus or minus 2 of those least significant bits. And at maximum or minimum, plus or minus 4 LSB, which, is not trivial. The gain error that we talked about can be really high. So here I'm talking about typical plus or minus 8 LSB and maximum plus 16 LSB. So it might as well be that those final bits of this particular DAC just don't exist, for example. They're kind of the noise. And then finally, I have some of my nonlinearity errors. So I have my INL here, which is typically much smaller. So plus or minus 1 LSB, max 4 LSB, and the DNL is plus or minus 0.5 LSB, maximum plus 3 LSB. So in addition to these errors, if I'm looking at practical usage of a DAC on a microcontroller, like the one on the Arduino DWE, I'm also interested in that clock frequency. So how fast I can actually change the output level of my system. And so in the case of the Arduino DWE and the microcontroller that's on that, the fastest I can output, and it's often called a sample frequency too, even though it's outputting things, which can be a little confusing, is about 2 megahertz, which means that delta t, that minimum time between conversions, would be 500 nanoseconds in this case.